Hey everybody, so today as promised I am going to go over problem number 3.2 from the Brueckner textbook, Lectures in Urban Economics. This is number 2 on the homework assignment, and it asks about the Harris-Todaro model of rural-urban migration, where we compare rural income to urban income or urban disposable income to see if people will migrate, right? So get my handy dandy dry erase markers out here. Remember that what we're going to see is we have urban income is Y, but disposable income is Y minus TX, where T is the cost associated with commuting and X is the distance from the central business district. And then rural income is just YA for agricultural income, right? Because we're not assuming that there's any commute cost because they live in a rural area. There's no distance from the central business district. And so what the Harris-Todaro model says is people are going to choose to move to the city if the urban disposable income is greater than the rural income. So the first question says that the amount of land needed for each household dwelling is 0.001, and the population is L. So the land required for one dwelling per the land required is one dwelling per person, or 0.001 L. And so we want to find out how much land is needed to house L people. And this is kind of like a problem we've looked at before. So let's go ahead and work it out. So if we have the amount of land needed for each household is 0.001, and we have a population L, then what we're going to need is that 0.001 times L quantity of space. Does that make sense, right? If we have L people and each person needs that much space, that's how big our city's going to need. Land area is equal to 10 city blocks and extends to the city's edge. So we can write the land area as 10x bar. And by setting these equal to each other, we can solve for x bar in terms of L. So what is that? That's the land area of the city is 10. X bar is the number of blocks. So it's 10 city blocks, or the land area is 10 per block, right? And then X bar is how far the blocks extend. So we set these equal to each other, solve for X bar. We get X bar is equal to 0.0001 L now, because we've divided both sides by 10, right? Now we want to add in the rural-urban equilibrium conditions. Okay, so the rural-urban equilibrium condition, remember, is a function of those two incomes. But the Harris-Todaro model also takes into account the fact that not everybody is going to get a job. So we can find the probability of getting a job by looking at that next equation, which says that expected income is going to be that urban income times the probability of getting a job, which is the number of jobs divided by the population. And then because we're looking at that disposable income, we want to subtract the commute cost for the city edge resident. And the equilibrium will occur when that's equal to agricultural income. So we've got the disposable income for a city edge resident that is expected based on the number of jobs in the population. If that doesn't make sense, you're going to have to go back and look at the slides a little bit and remember what we're talking about here. But it's just a modification of that that disposable income equation. So if we insert our city's edge from part A into here, we get that the expected income, YJL minus T, times 0.0001L is equal to YA if we're in equilibrium. So we can use this now to solve for the quadratic equation by setting the equilibrium condition equal to 0 and multiplying by L all the way through. So we're going to do some more math on the whiteboard, but hopefully that makes sense. We're going to set this equation equal to 0 and then multiply both sides by L. Okay? So let's do that. First, I'm going to set it equal to 0. So now it's 0 equals YA, right? Or 0 equals YJL minus T 0.0001 L minus YA. Okay? Does that make sense so far? So then you go through and multiply each component by L, and that's going to give us a quadratic equation. So I'm going to switch up the colors here again, because I think that pink might be hard to see. So now I've got YJL times L is going to be just YJ, right? So I'm going to multiply by L all the way through. So I'm going to get YJ minus T 0.0001, and this is also multiplied by L, so it's going to be L squared minus YAL. And so now you can see how multiplying by L gave us a quadratic equation, right? Where we've got A squared, or AX squared, BX, and C, right? So let me rewrite it in a way that you can see that clearly. I might need to bring my bigger whiteboard in here from the Zoom days. Okay. So the equation we're left with is that negative, well, here, let's write it the way we started it out with first. We've got YJ minus T 0.0001 L squared minus YAL. We can rearrange terms and get negative 0.0001 L squared T minus YAL plus Y times J equal to 0. Now, what we can do is substitute in an income given by the problem of $10,000, all right? Okay, so the book tells us that urban income is $10,000. We've also got rural income, YA, is $2,000. And we have T is now equal to 100, and J is equal to 30,000. So there are 30,000 jobs, commute cost is 100, incomes are 10,000 in the city and 2,000 in the rural area. So now we can sub those in and get a little bit of a cleaner equation, right? So now this becomes negative 0.0001 L squared times 100. So that's going to simplify that down to negative 0.01 L squared. YA is going to be 2,000 times L. And then here we're going to have YJ, which is going to be 10,000 times 30,000. That's going to be a little unwieldy, right? So what we're going to get when we add those in, give me a sec. Don't need the pen. It's going to be negative 0.01 L squared minus 2,000 times L, right? It's going to be 2,000 L plus 30,000 times 10,000, or 3. Cool? All right. Now we can solve this using the quadratic equation. Who remembers the quadratic equation? Not many people. You could also solve it with factoring if you want to. I don't care how you solve it. What you want to remember is the quadratic equation says that if you have ax squared plus bx plus c, you can find two possible values for your x by saying it's equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. So we can plug these coefficients. So negative 0.01 is going to be our a, negative 2,000 is going to be our b, and this 300 million is going to be our c. Okay? So we set it up, and that's how we do it. So let's go up here, and we'll just kind of keep reusing our space on the whiteboard, on this teeny tiny whiteboard. Okay. So x is going to be equal to negative b, which is negative 2,000, so 2,000, plus or minus the square root of b squared, which is negative 2,000 squared, or 2,000 squared, because the negative goes away when the square term is used, minus 4 times a, which is a negative 0.1, and c, which is that 300 million. I'm just going to run out of room, so I'm going to put all the zeros right there. Yeah, that worked. And then down here we have 2a. Cool? So you go through and solve that out, and what you should get is either negative 300,000 or positive 100,000. Since the city can't have a negative population, we find that the city has a population of 100,000. So the next part says, in equilibrium, what's the probability of getting a job, and what is the implied unemployment rate? And that should be pretty easy. So once you get to here, hopefully this is just plug and chug. If you get it wrong, go back, check your numbers, check your decimals, make sure you didn't drop a negative anywhere or anything like that. But you should get x is equal to, let's do this one, right? X is equal to negative 300,000 or 100,000. And that's going to be our answer. So when we have that information, we can find the probability of getting a job. Probability of getting a job is J divided by L. If J is 30,000 and L is 100,000, then it's 30,000 divided by 100,000, or about 30%. That's the implied, that's the probability of getting a job. The implied unemployment rate is just going to be the opposite. How many people don't have a job? Well, it's the other 70,000, right? So it's going to be 70%. The last thing that the question asks you in this problem is for part E to find the distance from the edge of the city and the commuting cost for the residents. Hopefully that's pretty straightforward too, right? You want to remember that the distance to the edge of the city is a function of the population and the number of blocks, right? We said that we could solve that back in the very beginning with this idea that there was that x bar was equal to 0.0001 L, right? So now we have our value for L, and so we can solve it by saying, okay, so if L is 100,000, X bar is 10 blocks. And then the commuting cost for an edge resident is just going to be T times L. Does that make sense? Hopefully it does. Hopefully that helps. Let me know what questions you have. And hopefully that helps give you a little bit of a better understanding of how the Harris-Tadero model works and how we can see these different factors play a role in rural-urban migration. Okay? Okay. So hopefully that makes sense. If not, let me know. Comment, email me, hit me up on the discussion threads. Otherwise, I'll see you next time. Take care.